Hello, everyone. This is Jing'e from Carnegie Mellon University, and today it is also my great honor to represent my previous colleagues Zhou Yang, Naxin, Yimiao, Yande, and Professor He Yuan from Tsinghua University to share their recent work, Satori, embed analog backscatter for audio transmission. In the question and answer session, Zhou Yang will be online to answer your questions. Audio sensing supports various industrial applications such as machine failure detection, security surveillance, and speech command recognition. To support these applications, we must first capture high-quality audio signals. Since audio signals attenuate fast and are prone to noise, a common solution is to deploy sensing nodes close to the audio source and transmit data to the server via wired networks. However, extensive cabling is usually costly and impractical in industrial settings. Thus, wireless transmission is preferred. However, traditional wireless nodes usually result in excessive battery weight and high maintenance costs, and we hope that the sensing nodes can deliver high-quality audio while minimizing the power consumption. So, backscatter is a low-power wireless transmission technology. Ideally, a backscatter tech can directly harvest energy from the environment, such as the solar energy or the RF energy, and then modulates audio data onto the backscattered RF signal. So this approach is promising to enable battery-free audio transmission. In recent years, researchers have proposed many backscatter technologies. Based on how sensor data is embedded, the backscatter can be classified into digital and analog types. The digital backscatter first converts analog sensing data into digital signals and embeds them into single-tone or ambient excitation. These methods can achieve throughput of hundreds of kbps or even several mbps, sufficient for audio transmission, while consuming minimal energy. In contrast, the analog backscatter directly embeds analog sensing data into backscatter signals. For example, the microphone array backscatter uses analog pulse modulation to embed audio into single-tone excitation. And lateral, our previous recent works, embeds analog signals into the CSI phase of Wi-Fi. Despite significant progress in backscatter, current implementations still face some obstacles in the audio transmission task. First, in audio embundling, digital backscatter can reliably process and embed audio signals, but brings complexity and higher power consumption. The analog backscatter, on the other hand, struggles to embed high-quality audio signals accurately. Second, since embed self-interface significantly degrades the audio quality, most designs choose to shift a reflected signal into a vacant, frequency band. However, this introduces additional energy and bandwidth overhead, which is often unacceptable in industrial-sized scenarios. So to address these problems, we propose Satori, the first embed analog backscatter for audio transmission. The Satori tag is excited by common Wi-Fi signals. It first uses analog phase modulation to embed audio signals into the phase of each Wi-Fi symbol, achieving fast, accurate, and low-power analog audio embundling. Furthermore, it tackles the self-interface and transmits backscatter signals within the frequency of excitation, reducing the energy and bandwidth overhead. Next, I will introduce how the Satori tech achieves analog modulation and embed transmission. First, we design a phase shifter for accurate and low-power analog modulation. The structure of the analog phase shifter is shown in the left figure. The microphone converts the audio into the varactor's bias voltage. As the voltage varies with the audio, the varactor's impedance changes and results in the reflected phase shifting. Since the varactors are reversely biased, the power consumption is negligible. The figure on the right shows the phase shifter's performance. The reflected phase changes linearly with the input voltage. And Satori leveraged the phase shifters to achieve accurate analog audio embedding while minimizing the power consumption. And next, we introduce how to achieve embed transmission with self-interface. Before detailing the scheme, let us first discuss the channel model in this paper. Let us first consider a backscatter channel, as illustrated in the figure on the left. The signal's path through the channel is phase shifted by the tag and then reflected to the receiver. The receiver performs channel measurements and the measured channel vectors traces a circle, which we call tuning circle. The tuning circle represents the backscatter tag's phase shift effect on the wireless channel. Next, we consider the embed backscatter channel model. Here, the RX receives the direct excitation and the backscatter signals, and the channel vectors still traces the tuning circle. However, due to the self-interface, it is impossible to accurately extract the phase modulation or the tuning triangle with a single channel measurement. So to determine this circle, the tag should provide at least 3 points with distinct phases. This is the basic idea of the embed modulation scheme. Now I introduce the design of embed analog modulation. When a Wi-Fi symbol comes, the tag first embeds a fixed reference phase in the first Wi-Fi symbol. Then the tag sequentially embeds the phase theta 1 and theta 2 into another 2 Wi-Fi symbols. These 3 Wi-Fi symbols form a triangle, which we call the tuning triangle. According to the geometry, its internal angles are functions of audio signal. Therefore, the analog audio signal is carried in the shape of the tuning triangle. Besides, since Satori uses 3 out of 6 symbols to embed 1 audio sample, the embedding rate is about 14.2 kHz and sufficient for audio transmission. We now consider embed backscatter transmission with self-interface. We can observe that the shape of the tuning remains unchanged. This observation confirms that the tuning triangle can reliably carry the audio signal in the embed backscatter transmission with self-interface. Next, we discuss how to extract the embedded audio on the receiver side. Since the tag modifies the phase of each symbol to embed audio signals, the receiver needs to perform pure symbol channel estimation to extract the embedded audio. Specifically, we leverage the palette subcarriers for the symbol level channel estimation, as they are fixed and known in every Wi-Fi symbol. For each palette subcarrier, the receiver extracts the tuning, computes the internal angles, and recovers the embedded audio signal. The receiver in process may seem straightforward. However, the carrier frequency outside causes continuous phase rotation, which distorts the recovered audio signal. And the deep channel fading can significantly attenuate the backscatter signals, leading to failure in audio recovery. We first focus on the CFO problem. Since CFO typically fluctuates around an average value, we propose a 2-step CFO calibration method. First, we remove the average CFO by leveraging the fixed reference symbols. The CFO introduces time varying phase to the fixed symbols. And we can estimate the average CFO using a linear fitting method. Then we eliminate fluctuating CFO by leveraging the cyclic prefix. Since the CP duplicates the last 16 samples of each OFDM symbol, we can extract the phase difference between the samples and correct the CFO symbol by symbol. After CFO calibration, the receiver can extract the tune-in triangle from each palette subcarrier to recover the text analog voltage. However, deep feeding may severely weaken some palette subcarriers, leading to the failure in audio recovery. To tackle this, we consider to extract audio signals from all palette subcarriers and apply weighted averaging. We assign lower weight palettes with deeper feeding. But how do we assign these weights? We observe that deep feeding reduces signal amplitude, which makes the tune-in triangle smaller. We calculate the sum of distance from the triangle's centroid to its 3 endpoints. This value reflects the triangle size and is leveraged as the weight. This method improves the audio recovery's robustness against deep learning. Then I will introduce the implementation and evaluation results. We implement a prototype on a PCB. For the embed analog modulation part, we only use 2 simple RF switches and 4 wire actors, keeping the power consumption in several microwatts. And we use the USRPs as the transceivers and the transmitter sends Wi-Fi signals generated by the MATLAB wireless wave. We use the following evaluation setup. The TX transmits Wi-Fi packets at 20 dBm. The tag was placed at a default distance of half a meter from the TX. The TX, RX, and tag were all equipped with 6 dBi antennas. 2 speakers adjacent to the tag generated audio signals ranging from 200 to 3600 Hz. To evaluate Satori's audio transmission quality, we recorded the tag microphone output at 320 kbps as the original audio signal. And we measured the signal noise ratio of the recovered audio signal relative to the original audio signal. We can find in indoor environments, we evaluated the audio SNR transmitted by Satori and varying tag to RX distance in both line of sight and NLOS scenarios. The results shows that Satori supports transmission range of 35 meters and achieves an SNR exceeding the 18 dB. We also evaluate how Satori's in-band transmission affects Wi-Fi traffic due to the backscatter signal being much weaker than the original Wi-Fi signal. Satori doesn't significantly impact Wi-Fi traffic in most scenarios. Notable good put directions occurs only when the modulation and coding scheme is higher and the tag is positioned as close as 5 centimeters to the TX. However, such extreme conditions are rare in real-world deployments, especially in industrial settings. Therefore, Satori doesn't significantly impact Wi-Fi traffic. We also implemented several proof of concept applications. We transmit the mechanical sounds and human speech, and then perform machine failure detection and speech recognition on the received audio. The result shows that received audio can be accurately recognized. For example, at an SNR of 6 dB, machine failure detection achieves 95% accuracy, indicating the abnormal mechanical noise can be accurately identified at a distance of 35 meters. Thus, Satori efficiently supports the audio sensing task. So, in summary, we propose Satori, an embed analog backscatter that enables ultra-low power audio transmission. Satori transmits audio at about 14.2 kHz sampling rate, achieving SNR exceeding the 18 dB, and supports transmission distance more than 35 meters. Satori follows the paradigm of RF computing, offering a direct manipulation from the analog audio to the phase of RF signals. This enables low power audio transmission and opens new possibilities for IoT audio sensing applications. So this is our work, and my colleague Zhou Yang will be for the question and answers. Thank you.
Any questions?
Thank you for the presentation, and I'm EJ from National University of Singapore. I have two questions. The first question is that I noticed that you use the channel modeling to transmit your audio signal. So I'm wondering that if your tag can support the mobility. The second question is that I'm curious about will the frequency of the audio affect the performance of your recoveries through the backscatter tag? Thank you.
Thanks for your questions. It is a very good questions. If I understand correctly, you have two questions. First, the questions is first about channel model, and after that, sorry, I don't know very clearly. And the second question is about the audio privacy problem, right?
I think the first question is about the mobility, and the second question is about your recovering. What's the impact of your recovering audio frequency?
Okay, well, first about the channel model. In fact, we first remodeled the in-band backscatter channel, and we just what we showed in our paper and in the PowerPoint. We first find that in fact the backscatter's modulation can be regarded as a modulation on the transmission path or the channel. So using the channel model, and we designed our novel in-band analog modulation. That is the basic idea of our the motivation or the basic idea of our channel model. And the second problem of the audio privacy. First, the most important scenario of our design is in the industrial audio sensing. And as for the audio privacy problem, it is a very interesting problem because if we deploy such a Satori tag in the meeting room or something we care about the privacy, it really can be used to off streaming, and this is also a very interesting application. That's my answer.
Okay, thank you.
Okay, let's thank the speakers one more time.
Thank you, Zhou Yang.
Okay, thank you for listening, and thanks Gino to present my paper on my behalf.